So are there any questions before we get started? Because it's because there's this exciting Mars rover landing last week. I think the NASA released a video from this rover as it was descending through Mars's atmosphere and landing. Kind of the first time I think I've ever like almost like it's just strapped a GoPro to the
The navigation has confirmed that the parachute has deployed and we're seeing significant acceleration in velocity. Our current velocity is 150 meters per second at an altitude of about 12 kilometers.
What are you doing?
Perseverance has flew subsonic speeds and the heat shield has been separated. This allows the cameras to get their first look.
Come on, your camera.
Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Why is that showing my camera for? That's a video.
so as a parachute, it's burning.
Class,
It's falling pretty quickly because Mars atmosphere is so thin.
6.6 kilometers of the surface.
dẻo cỡ mày à.
Continuing to descend on the parachute. We're coming on the initialization of terrain relative navigation and subsequently climbing.
What are you doing?
About 90 meters.
What are you making?
At an altitude of 4.2 kilometers. We have confirmation that the wind emission system has produced a balanced
Your class at 12:30, no?
terrain relative navigation. We have timing of the landing engines.
So now they're starting to fire engines to slow down the descent.
Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. The confirmation that the backshot has separated. We are currently performing the diverse maneuver. Current velocity is about 75 meters per second at an altitude.
What are you doing here? What are you munching on? Huh? Oh, that jerky.
Their terrain relative navigation. Current speed is about 38 meters per second, altitude about 300 meters off the surface of Mars. We've started our accordion, which means we are conducting the five-phase maneuver. Practice maneuver has started. We're 20 meters off the surface.
So it's hanging by a bungee cord now in order to so that the thrusters don't pull up.
Touchdown confirmed. Perseverance, on the surface of Mars, ready to begin digging again the pathway.
What are you
So anyways,
doing?
that was very cool.
Bad boy. Missing work, please.
Okay. Yeah. So the idea is that it's very hard to land something on Mars because you can't just use a parachute because the atmosphere is so thick that you go too quickly. So we're still sharing it.
The heck you got a spoon for? Oh, ice cream?
Something else, guys.
You were opening a baggie? Oh.
So the idea is that it's so hard to land on Mars because the atmosphere is relatively thin. So they started with the parachute, then they used thrusters, and then the thing with the thrusters lowers down the
Is that baby still around?
basically, so that you don't hit the thrusters and props and stuff. So it's kind of remarkable that it worked. So if there's any questions on Mars, I'm not an expert on Mars, but if there's any questions.
Where's the most ice cream?
There's only that one.
Okay, then our agenda today is to start talking about the children. Two of the inner solar system terrestrial planets, right, have solid surfaces. And now we're going to talk about the outer planets past the frost line, where for reasons that we explained before, but we'll go over it today. These planets are going to grow much larger and have different composition. So, first of all, a reminder of all the planets and how they're situated relative to the inner terrestrial planets Mars here. Mars is about 50% further from the sun compared to the Earth. But then you start jumping huge distances, right? If you think it's hard to get to Mars, Jupiter is much further between Earth and Mars. And then Saturn is twice as far as that. Uranus is twice as far as that again. Neptune is 30 times the distance from Earth to the Sun. And then also just other basic orbital characteristics is that as you get further from the sun, it takes longer and longer to orbit the sun. So while a year is 1 year for us on Earth, it's like 80% longer on Mars. You get out to Neptune, it's 160 years, Earth years, for Neptune to orbit the sun.
The hell are you eating?
And just to visually see how
Eating drugs?
as large as its orbits are, right? These are all the terrestrial planets out to Mars in red. Look at that. It's very, very far away. And then it's another huge jump to Saturn, another huge jump to Uranus and Neptune, and there's also Pluto. And again, now these interterrestrial planets are in this tiny little region in the very center. Okay, so there's huge difference in distances.
The heck?
And here are the Jovian planets in terms of their relative sizes. Jupiter is about 5 times the distance from Earth to the Sun, and we just went over that. Saturn is twice as far still, and Uranus is twice as far still. So Jupiter is about 5 times the distance all the way to Neptune is about 30 times the distance. The sizes, Jupiter is about 11 times the Earth's diameter, so that's the largest of the planets. Saturn is not far behind. You can see visually here. Saturn is about 9 times the size of the Earth. Both Uranus and Neptune are similar in size, about 4 times as much. In terms of mass, there's really no comparison. Jupiter is by far the most massive, over 300 times Earth's mass. Saturn is about 100 times Earth mass. Uranus and Neptune are still much larger than Earth mass, about 15, 20 Earth mass. And they're all much less dense than Earth. So I'll see a picture of this in a second. But they're all hovering roughly around the depths of water.
What are you eating? Let me see. What is this?
No.
Let me see.
They're all much
Is it really
cooler than
candy?
temperature on Earth. Temperature on Earth is close to 300 degrees
There's no ice.
on average. Here, this
There's no ice.
temperature at the surface of Jupiter is freezing.
It looks brown.
And it only gets cold
Eating
when the
chocolate.
sun.
Let
And
me
they're
see.
all
No.
tilted in
No.
such a way that they are rotating
No, right. You know the little,
counterclockwise.
this is what you showed me yesterday. You showed me a little baggie full of the Hershey's.
Kind of tilted on its side, so we call that 90 degrees. Tilted on its
You're
side.
eating Hershey, diabetes.
Clockwise or counterclockwise.
You really got diabetes, man. You really want to do needles soon? You really
Yeah,
want
so
to
here's
do
the
needles
picture
very
showing
soon.
comparison of the densities, where it really shows this pattern of composition. The interterrestrial planets are all dense. They're all close to 4 or 5 times the density of water. But then you get past the frost line, right? You have the asteroids and then the frost line where past which, remember, in the early formation of the solar system, it got cold enough because you're farther away from the sun.
Why are you coming over here? Go away.
Less dense materials could freeze out. Stuff like ice, hydrogen, helium can be captured by these big ice-rich objects out here. And there are more stuff in the solar system is ice and hydrogen and helium than the terrestrial materials. And all of that is less dense. Hydrogen is light. So all of these things in the outer solar system, including the comet-like stuff in that past Neptune called trans-Neptunian objects, are much less dense. That reflects their different compositions. The composition of these Jovian planets.
Why are you eating chocolate? You already got diabetes, yo.
Still eating.
You're gonna go this one soon. Yeah, you're getting there soon.
Because they're the simplest elements that were created during the Big Bang.
You're already getting there.
Next, you have things with lots of hydrogen in them.
You're getting to needles very soon.
Ices because they freeze. Water, ammonia, methane, all things with hydrogen in them. Very common.
Eating straight up chocolate like that isn't that
So these are things that were very common in the solar system until past the frost line. You can form stuff that'll freeze.
You're going there.
Ices. There's more of it.
You're eating straight up sugar right now.
Then have a lot of gravity that can pull in hydrogen and helium to make them even bigger.
The ice cream in my mouth is good.
So the composition, not going in finer granularity, your Jupiter and Saturn are both hydrogen.
It's getting a little
They have cores that have hydrogen compounds and then also rock and metal in the cores. Now the cores of all of these planets are terrestrial. The cores contain metal and rock, but it's just outside of the cores is way more proportionally more hydrogen compounds. And then the cores of Saturn is mostly hydrogen.
You're not you?
Uranus and Neptune.
I know my Bible ice cream, but not like that.
More hydrogen ices. So lots of water, methane, ammonia. And then again in the cores it's still.
How did you put it?
How did I put it?
Get the boba straws out.
So here's a if you
Is the boba straw frozen?
various planets. The terrestrial planets.
Mommy, no touch my food.
No.
A bar with not very much height. It's blue because this is heavy elements and stuff. Rocks and metals. Okay. But as you can see here, Jupiter, Saturn, Uranus, Neptune, they have more terrestrial material, right? But we don't call them terrestrial planets because they also have huge amounts of hydrogen and helium. Okay. In particular, Jupiter and Saturn are almost all hydrogen and helium. Uranus and Neptune have more hydrogen and helium than there's mass in terrestrial planets, but still they also have lots of other stuff. So just to explain what we went over a few lectures ago, we talked about the solar system formation, right? What happened? How did we get these large Jovian planets? They're so different from the terrestrial planets. Well, you have to remember that hydrogen is just way more abundant than everything else in the solar system. But it was only past the frost line. You get farther from the sun, things cool down. Frozen hydrogen.
What the heck?
Hydrogen ice. Since there's more of that stuff.
Don't turn it on, man.
And with those huge ice falls,
But don't turn it on.
you can start pulling in hydrogen. They grew them even larger.
Don't turn the computer on.
The first ones to
They're
capture
charging.
hydrogen
Don't turn it. Why was they like that?
for Neptune and Uranus, which
Yeah, I killed it. Okay.
all of the cores of the Jovian planets are pretty simple. They're all
I don't want to.
right, worth of terrestrial material.
You give me a little wipe and let me check my blood.
And lots of ice. Okay, but then it's the differences between them are that Jupiter and Saturn then captured a huge amount of hydrogen and helium, and then the leftovers were gobbled up by Uranus and Neptune. Didn't get as much hydrogen. Now, the explanation for why these planets get gas giants and have all this hydrogen helium comes back to this diagram that I
Here's a-
explained last lecture.
Give me one.
Where it tells us
Give me some banana.
that
You
on a planet that doesn't have
I need to dollar.
You want to check your blood?
No.
Yes.
to gas, right?
How
So it doesn't
sugary
have
are you? 200? Huh?
It's pretty small.
No, not 200 baby.
Just let me see how many hundred you are.
No.
Just let me see.
No.
You need to see. Look, you're getting the needle to the stomach, girl. Better. Wait a second, see that?
I think I forgot you in 2 hours.
No. Let me do you now.
No.
Let me see you
You
now.
won't even be right.
I'll check you after pasta. Huh?
Pasta.
Yes.
I love pasta.
Give me that fat finger.
Okay.
Please.
No, not this one. Middle finger.
Are you stick the middle finger in me now?
Yeah.
And that's why they are gas giant planets. They hold on to what
Okay.
they so
Middle,
Stick
please.
the middle finger in me.
Yeah.
You ready to squeeze?
so
What is arrow?
Y-axis
Oh.
are also important as if they were too
Did I
hot,
get ya?
those gases can go far away from the sun, so it's cold. Okay, so why did Jupiter and Saturn capture more hydrogen in gas? They're closer
Any
to
blood?
the sun, they're closer to the denser parts of the nebula.
Come on, give it.
Also,
Give it up. Give it up.
they formed early because that was the denser part of the
Sweet.
nebula. So they
Wait,
captured most of the hydrogen and helium.
Not enough.
It's okay.
Don't get
Solar
in.
wind,
What?
solar wind blew over
I'm
the
okay.
planets.
It didn't get through. Not enough blood.
Essentially, what
It's okay.
that means is that you're
So I'm gonna check you again.
It's okay.
One more time. Give me that finger.
Okay.
Give it.
Okay.
Don't here.
Oh.
There.
There's just a
Okay.
couple questions to make, to make
That's
sure
okay.
you're following along. So one question would be, why did the Jovian interiors differ? Well, it's because accretion took longer further from the sun, because there's less material
Better.
further from the sun. So the
Better.
distant planets
Better,
formed
better.
their cores later, right? All that stuff, the big ice cores have enough gravity to pull in hydrogen, right? So they captured
Squeeze,
less
squeeze,
gas.
squeeze.
I don't know where the puncture is.
Now another
No blood.
interesting feature
Cup
of the
again.
planets is their density. Okay, so
Hey,
first
let
of all,
me
Neptune and Uranus, remember, they have less hydrogen and helium.
guys, you see that the
So these
finger.
dense stuff,
Pick them up and that comes
they,
out.
as you'd expect, are
Hold the
denser.
other fingers.
No.
A bit denser, for example, than Saturn. But strangely, Jupiter. is
Give me that index finger.
No.
Saturn is less dense because it has more hydrogen and helium than Uranus and Neptune.
Better, man.
Why does Jupiter? Why is it suddenly more dense?
Next thing you say will make me
Well, the
do it.
answer is
Give me that super finger,
So,
man.
that it's
Better.
to actually have so much gravity that
That
it
you
can
can get me pasta.
compress.
Oh, pasta.
So it's kind of
Are
like
you gonna give me the finger yet?
I don't know. We're not.
Yes.
at a certain
Oh,
point,
that's
start
good.
adding pillows
Middle, middle, middle.
Stop looking.
below it.
I know that you're gonna do like a middle.
Better,
Lying to me.
man.
You're lying to me.
Oh, give me the middle finger. Come on.
There you go.
Are you-
What? I'm doing this so you don't put any other finger.
Give me that finger. You look to the fire your thumb
Adding
there.
accents.
There, give me that middle finger.
Ow.
So Jupiter is actually close to the
Give me
planet.
that
Oh,
blood.
shoot, blood.
Is it enough for me? Squeeze, squeeze, squeeze.
I don't know. I'll poke you too.
Press the gas.
Squeeze.
Smaller. So it's actually kind of a counterintuitive result. It's true.
Squeeze. Squeeze. I need to squeeze
Add
more.
gas to it actually press smaller.
Not yet. There.
So
Get
that's
in
why
there.
Jupiter is
Yes. Perfect now.
closely smaller, given that
We
it's
got to it.
more than 3 times the mass of Saturn. It's only a little
Pretty
bit
high.
So low.
146.
What that means? I'm fat?
Yeah, you're fat.
Okay.
You're too fat.
Check your blood.
So
You want me to check my butt?
why is Saturn
Oh,
almost as
wow.
big as Jupiter, but having less than 3 times the mass? It's because Jupiter has the ability to compress its gas form due to its greater gravity, which increases its density. So putting together, right, a lot of what we've talked about, right? So remembering that in the most of the stuff in the solar system is hydrogen and helium, right? The Jovian planets have a lot more ices
you
than
get
the
both yet?
planets, but
Nó
even more
cho
hydrogen.
kết thúc đó ha.
Keeping that in mind,
I'm
what
ready for
is
you to get
overall Jupiter's composition most like last this one?
I'm ready to wear that screen. Wally!
Yeah.
Why not do it for you?
No. Most. It's not most of Earth. Comet.
Wow, 3 little punctures on my finger. You're so evil.
The comments.
Give me 5 more seconds.
The comments.
Okay. Okay, most people correctly said the sun. The sun
Did you
is
get both?
primarily
Oh,
composed of
that's the
hydrogen.
sun. Huh?
And
Yeah, I
Jupiter
thought it would be the
is most
sun.
of its mass from hydrogen. So
Get hooked
Jupiter's
double
composition is most like that of the
That's
sun.
evil. You know that? I'll poke you too.
If you're going to
Oh,
go
you like
next
what?
after the sun,
I'll get poked too. Give me a finger now. Now! Okay, then another one. Go there.
Go away.
It's most like
You
the
wanna
sun,
what?
which is
You
primarily-
wanna what? Get your finger poked too. Once. You have to. Okay, then another one.
You
Okay,
got
now
too
what
much
about
blood
the
squirting
interiors
out,
of the
huh?
Jovian planets? They're kind of interesting.
Mean.
Not me. If you
Because
wanna watch, you gotta pay for it.
as you go inside of a planet,
Hey, what?
the
Oh my
density
God.
Your baby things up. Give me.
and also the
Why?
temperature changes.
Cause
125.
Increase. So while you have these clouds on this near the surface of the Jovian planets, and huge amounts of gaseous hydrogen, eventually pressure goes down. And below that,
Mine are good. You are bad. Oh my God.
so it's not that these gas giants are just gas all the way through. It gets
Ah!
okay.
densest rocks. But there's no solid surface. It's kind of a continuous transition as you go through the river.
You cut him? What you do?
I tried to get away from it. I don't know what you're trying now.
Because the runs massive
What? What's it?
from the hydrogen solid cloudy hydrogen. And
Have you seen your back? Have you seen your belly?
center of that you have a core.
Not even that.
So those
That's
are
some of this stupid idiot. This is plastic. Plastic. How? How did I? I told you to drop it. Stop it now. Don't shoot.
they get warm from the sun, but remember they're pretty far
Come
from
here.
the sun. Part of their energy, in fact,
You don't need a band-aid. What you doing?
You got a little scratch from this to the plastic.
Just don't have a band-aid. No
That's
need.
stupid.
Shut up. You don't need a band-aid.
He is bleeding now.
happens
No, he not.
continue to contract under gravity. They don't just contract right.
Wash your hands up. Wash your hands up.
Don't touch this.
Potential
Wash your hands. Get it clean.
that wants that right hot
It
stuff
ain't doing
expand.
it. See, this is plastic. Plastic can cut you through.
As long as it can heat itself up by contracting a little, it just takes a very, very long time.
Do not touch this ever again.
So
You wanna get her again?
you're actually very warm on the
Don't
inside,
touch plastic.
just like
Don't
the
touch
rest
this ever again. Okay, you promise?
okay, good. All of them have similar pores. Once you get down to the very center, they have like thin earth mass.
Push the boo-boo long bye-bye.
Metal,
Okay, so two.
ice balls. The difference is around the
Promise not to touch
one
it?
of those pores could draw in most of the solar system's hydrogen outside the sun.
Do not play with this.
Okay, so let's look individually at each of
Plastic and crackers, you want to
closer. So Jupiter, mostly hydrogen and helium.
So that's for plastic, okay? Did it hurt? Did it hurt? Okay.
Closest to
Let's go.
You're gonna go plastic like an idiot.
You're falling.
Okay? Okay, okay.
Size of the Earth.
Yeah.
As huge numbers of moons are still discovered.
You're falling.
Cataloged it for that 79.
No plastic, okay?
What did you even grab it from him for?
So
You're falling.
So this is the sort of a picture you'll get of the ground-based telescope. Of course, it has its great red spot. It's known for its beautiful streaks. That we'll talk
You write your 146 down.
yellow and white colors. Of course, now we get
You write your 146 down.
probes out fly past Jupiter. We've even gotten probes to fly past the surface of Jupiter's moons. This one's Io. It's volcanic. So here you see Io and then Jupiter with Jupiter does have a ring. You know, shadow has this prominence in the solar system. And we'll talk about the Jupiter's moons. If we go down below the clouds of Jupiter, right? So you have the cloud tops that are freezing cold. But as you descend, first of all, the temperature rapidly increases. You don't even have to get very far before the temperature is as hot as the surface of the sun. Truly, never gets hot to cause fusion like that in the center of the sun, but it does get up to about 20,000 degrees. As well. The pressure is
I let you go 3 times. That means 3 servings.
over 100
Yeah.
times.
You did 3. You drink this one. Huh?
No, you stabbed me 6 times. I almost.
Then get your stuff out.
You already know what to do. You can do it yourself.
Water, the surface has these very, non-dense clouds. But once you get towards the center, the density becomes 25 times the density of water. Another interesting thing about Jupiter is it has an incredibly strong magnetic field. Okay, look at the size. So this is the Earth's magnet. We talked about Earth's magnetic field, how it protects us from the solar wind. This is Earth's magnetic field magnified by 10 times, and it's still dwarfed by Jupiter's enormous magnetic field. And because of its strong magnetic field, and because you have charged particles from the solar wind and also gases escaping from like volcanoes on one of its moons, Io, you actually get auroras that we can see. All right, so this is a visible light picture of Jupiter, but we use ultraviolet light photographs to show the intense auroras you get on the poles of Jupiter, just like you have on Earth to our magnetic field. Okay, you have lots of weather on Jupiter. So on Earth, right, we have storm systems that tend to, first of all, on Earth, they tend to be low pressure systems. So meaning if you go look at the center of a hurricane, it's a low pressure in the center, which means that you're drawing winds toward the center because you want stuff to go towards the low, high pressure goes to low pressure. And then there's something called the Coriolis effect, which is because the Earth is rotating, stuff near the equator is moving faster than stuff near the poles, right? Because if you're a wind going around the equator, you have to go around fast as the Earth is rotating. But if you go towards the poles, you don't have to move as quick. So that causes this thing called the Coriolis, of course, which means if you have winds moving towards the center of this hurricane, they get deflected because winds coming from, if you're in the northern hemisphere, winds coming from the south are going too fast. So they end up being deflected so that they end up rotating counterclockwise. Whereas in the southern hemisphere, they rotate the other direction. So that same effect explains the rotation of, for example, this enormous storm, the Great Red Spot on Jupiter. Now, this is in the southern hemisphere of Jupiter, and it's a high pressure system. And so if you have a high pressure system pushing the storm outward, and you're in the southern hemisphere, and Jupiter's rotating counterclockwise, you expect this thing to be rotating counterclockwise. Coriolis, so that's what you see. So this is an enormous, basically like a hurricane on Jupiter that's been around since we've seen Jupiter. This is such a large storm, much larger than Earth, that it's going to be lasting probably for another 100 years. Now, of course, you also get these really beautiful colors and streaks of clouds and so on across Jupiter, including the Great Red Spot, right? So you see in this picture here, you have streaks of white, orange, red. This is because, right, remember,
What's up, Yui?
Jupiter, the temperature, just like on Earth, actually, the temperature in the atmosphere changes depending on different altitudes.
I don't got your red notebook.
It's coldest at high altitudes, and then you get lower altitudes, it gets warmer. And different molecules in Jupiter's gaseous atmosphere.
Oh, now go,
can
please.
form
See
ice
you.
at different depths. So furthest out, when it's really cold, ammonia forms clouds. Those are kind of yellowish white, but kind of yellowish. And then you descend further, and you get ammonium hydrosulfide, which is kind of orange cloud. You go further, and then water forms clouds, which is warm. It's warmer, so that's finally where you only see water forming clouds. And so at these different altitudes, you have different cloud systems. Some ammonia, some ammonium hydrosulfide, some water. Water's white, and so that's what's showing all of these different patterns or different altitude systems of movement in the atmosphere. Very similar to what you see on Earth. Of course, on Earth, we just mostly have white clouds. But of course, the white clouds are kind of moving. We have these weather systems. Well, Jupiter has similar weather systems at different altitudes. They're different colors. And it makes these really beautiful patterns. Saturn is similar. Okay, Saturn also has similar patterns on its surface. And it's a similar planet. It's mostly hydrogen and helium like Jupiter. Twice as far from the sun as Jupiter. About 100 times Earth's mass. And also like Jupiter has a huge number of moons. And also like Jupiter has rings. All of these Jovian planets have rings. Saturn is unique in that it has just the most beautiful and prominent rings. So we'll talk some about those in particular. But like Jupiter, 80 some moons, okay? But there's probably more we keep discovering. Here's a nice flyby that one of our probes did showing the rings of Saturn. In fact, if you fly by directly side by side or directly level with the rings, you can hardly see them because they're so incredibly thin. Here's one showing it's Titan's. Saturn's largest moon, Titan, passing Saturn, and it's kind of eclipsing Saturn as its shadow. Here's a nice picture that has 5 moons in one picture and Saturn's rings. So here, actually, Saturn is off to the right. You don't see Saturn, so this you see. This is from the Cassini probe as it passed Saturn. You see Janus, Pandora, which is kind of in the rings, Enceladus, Mimas, and Rhea here. So going further out, we have Uranus. Now we're another twice as far as Saturn, 20 times the distance from the Earth to the Sun. Remember, Uranus is kind of tilted on the sides. That's what you see in this picture. It's rotating, but it's on its side. And it also has rings, and those are on its side too. And they're showing up as red in this picture because it's a superimposed image. The rings are so faint that we need to take long exposure photographs of the ring, and we did a false color image of them and added them to this picture so that you can see both the rings and Uranus together in one photo. So all of these Jovian planets have rings, including Uranus. Also lots of moons. We've discovered at least 27 moons. Here's Uranus with one of its moons. Ariel is most prominent here. And then also, again, a superimposed image with its rings. Here's another picture also showing that Uranus has a magnetic field because it has an aurora. You can see it moving around as it rotates around over the course of a month, 2011. Neptune, okay, also looks similar to Uranus. We're going to talk about the color in a moment, but so similar to Uranus, okay, it's made of mostly hydrogen compounds, a lot hydrogen and helium, but a lot of hydrogen compounds, and that's what's different from Uranus and Jupiter. Again, very far, 30 times the Earth's sun distance. Like Uranus, it's about 4 times the Earth's radius, about 7 times the Earth's mass. You see that we're discovering fewer moons of Neptune, but that's only because it's so far away. It's probably also has many, many dozens and dozens of moons, but we've discovered at least 13 of them. Remember, it has its moon Triton is unique because it has what we call a retrograde orbit, orbiting in the opposite direction from all the rest of the things, the patterns of motion of the solar system. Neptune has seasons, and because it takes 160 years for Neptune to orbit, it's the planet with the longest orbital year. Those seasons last for years. Okay, so here's just showing the development of different seasons. There's an average as we watch Neptune rotate. We kind of take an average of what the cloud tops look like as they get colder in different seasons. You get different ice crystal formation in the atmospheres. So here's between 1996 and 2002, you're seeing the development of a change of seasons on Neptune. This is from the Hubble Space Telescope. Here you can see the cloud tops showing up in kind of whitish in this photograph as Neptune rotates from Hubble. So it's a little blurry, so far away. But we have sent probes, so here's better pictures, again with a superimposed image of the rings. And then here, as you from Triton. Now, what gives both Uranus and Neptune this kind of characteristic blue color? It's because of methane. So methane absorbs red light and transmits blue light. So remember, light of all colors comes from the sun. So you can think of, say, red mixed with blue coming from the sun. But the gas on the from methane, and remember, methane is a hydrogen compound. It's one of these common hydrogen gases that you see on Uranus and Neptune. It absorbs red light, and then that blue light that's remaining is what gets reflected back into space. So that's why they look blue. And then you see various clouds forming in the atmosphere. Methane clouds tend to be kind of whitish, so they're kind of whitish clouds reflecting blue light. Now, one of the most interesting sets of moons in the solar system come from Jupiter. Okay, let's talk about the Jovian moons, meaning all the moons of the Jovian planets, and there's many of them. Here's a kind of a selection of the larger ones compared to, say, Earth moon. So here's the size of Earth moon. But you look, there's some really large Jovian moons. So these are the 4 what we call Galilean moons of Jupiter. We'll spend some time talking about them. They're all about as large or larger than Earth's moon. And they're very interesting. Titan, Saturn's moon Titan is larger than Earth's moon. It's very interesting. Neptune's Triton is almost as large as Earth's moon. And so one thing to remember is that because these Jovian planets have so many moons, a lot of them are probably just captured asteroids. So we call these irregular moons. Irregular moons have more distant orbits, they tend to be less circular orbits, so we call that eccentric. They're less in the ecliptic plane, so we call that inclined orbits. Some of them are orbiting in the wrong direction. We don't call these major exceptions because they're just little moons. They're these captured asteroids. Whereas regular moons tend to be the ones that are larger. They're orbiting closest to the planet. They're in the ecliptic plane. They're all orbiting, following the patterns of motion we've talked about, circular orbits. And they probably formed during the formation of all of the planets from the planetary nebula itself. And so we're mostly going to be talking about the regular moons, which tend to be the larger moons. So the larger moons have enough gravity to be spherical. So especially these important moons we'll be talking about today, they're spherical. They have a lot of ice, and this will be interesting because some of them will actually have, we think, liquid water. And they tend to all follow these patterns of motion, circular orbits in the same direction with the planets rotating in. But there's many, many small moons, probably far more than we can see with ground-based telescopes. So we're going to continue to be discovering them. And they're often just potato-shaped, basically captured asteroids. So here, if we look at Jupiter's regular moons, the important ones are called the Galilean moons. Okay, Io, Europa, Ganymede, and Callisto. These are remarkable because actually, I mean, you can see these with just like a cheap backyard telescope. So here's a picture from a cheap backyard telescope. You see Jupiter and these 4 Galilean moons. They're called Galilean moons because Galileo saw them with one of the first telescopes around 1600. So here you see these 4 that I'm talking about. Io, so it's closest to Jupiter, then Europa, and Callisto. What these numbers are showing is that there's something interesting about these moons. They're close enough to Jupiter that they have significant tidal effects. Remember, the tidal effect is that Jupiter's gravity is tugging a little bit more strongly on one side of it than the other. That causes it to be able to tug on the planet in ways that allow it to kind of synchronize the rotation, the orbital rotation of the planet, potentially so that the planet is rotating in some synchronous rate compared to its orbit around its parent planet. We see this with our own moon, and we saw this with Mercury. Another kind of similar effect is if you have moons that are bunched up together, they themselves can resonate with each other. That's what you see here with Io, Europa, and Ganymede. That is, for every 1 orbit of Io, you have exactly 2 orbits of Europa and exactly 4 orbits of Ganymede. Okay? And that makes sense because that generates a pretty strong tidal effect that we're going to talk about. Because what that means is that every 2 orbits of Europa, you get an exact alignment with Io, which causes the same tug on the moon over and over and over again. So we'll come back to that in a second. But one thing to point out is that these 4 Galilean moons make up 99.997% of all of the moons orbiting Jupiter. So really, these are pretty much everything when it comes to the mass of moons around Jupiter. So let's talk a little bit about they're called the Galilean moons again because they're discovered by Galileo in 1610. There's pictures of them in order. So Io, Europa, Ganymede, Callisto. Io has active volcanoes. We'll talk about why it's so warm in a second. But also more extends to the other planets, Europa, Ganymede, Callisto, all of which may have subsurface oceans, which mean that they're remarkably suitable for life. So here's kind of showing them all on one page. We'll go a little bit more into each of them. So Io here, extremely volcanic. See, it's kind of just surface. Looks like you might see volcanoes on Earth, very sulfurous, lots of interesting colors, lots of active volcanoes. Europa is interesting because, this does not look like a cratered ball like moon, like our moon, right? Because remember we talked about, you don't see craters, that means that there's something happening on the surface to behave. We would say it's geologically active, right? So Io, of course, is geologically active. It's covered in volcanoes. But you see the same thing with the other Galilean moons, Europa, Ganymede, and Callisto. They're also geologically active, but we would call this ice volcanism. Here you see these crisscrosses, like these tectonic plates, but these are ice flows shifting on the surface of Europa, which is a similar thing that's happening in Ganymede and Callisto. Callisto has more, is less active. It's the furthest from Jupiter and it's less warm. But there's still a lot of fewer craters than you'll see on something like that. So here's a picture of Io, very, very volcanically active. Here's a beautiful picture from Voyager as it passed Jupiter. So it's flying by Jupiter and we see this wonderful picture of Io in the foreground. Here's kind of an ice ball, cratered ice ball, Callisto, captured fairly up close. Europa captured up close. Again, you don't see much craters. What you do see are these stripes of kind of breaking, freezing, and defreezing and refreezing ice flows on the surface of Europa, and no craters because it's active and full of ice volcanism. That is similar geology to if you have magma flowing underneath this ice, but instead it's not magma, it's liquid water in the case of Europa. You have liquid water flowing underneath, and then basically icebergs breaking and forming. So let me talk again about this tidal effect. This is called tidal heating that warms up these moons. So even though they're so far from the sun, they're actually really warm. Well, at least Io is very, very warm with all of this volcanism. Europa is warm enough to have a big subsurface ocean. And we think similarly, Ganymede and Callisto also have subsurface oceans because they're warm deep down with this tidal heat. So let's talk about this. So one thing is that Io, the closest moon to Jupiter, has kind of an elliptical orbit. Now, it's close to Jupiter. Jupiter is huge, so it has a very strong gravitational tidal force on Io. And because it has an elliptical orbit, that means it gets squished and pulled more as it moves around Jupiter. And that basically causes it to flex and strain. So you're essentially having friction on Io that heats it up internally. That causes a tremendous amount of tidal heating, causes it to be very volcanic, even though it's so far away from the sun and even though it's very small. Otherwise, it would have cooled down by now, but it's kept warm through this tidal process. And then there's this, right, it's able to have this elliptical orbit because of this tidal resonance we talked about, this orbital resonance we talked about, where for every 4 orbits of Io, you have 2 orbits of Europa and 1 orbit of Ganymede. And what that means is every 7 days, it gets tugged in the same direction because all of these moons line up in the same direction. So it keeps getting tugged in the same direction, which gives it that elliptical orbit, which gives it such a strong tidal heating. And the same sort of process tidally heats to a lesser extent Europa, keeping it warm on the inside so you can have subsurface oceans, and Ganymede, and even Callisto. So we think that now Europa has a thick layer of ice on the surface, okay? And we can't see below it, but the evidence seems to suggest that below the surface is a vast liquid ocean of water. So life on Earth, we think, formed initially underwater, near hydrothermal vents. That's a source of energy. So eventually, life learned to photosynthesize to get energy from the sun. But the first thing that happened was that life started getting energy from around hydrothermal vents deep in the ocean. So if this is true as we understand it on Europa, there's just as much chance of life existing on Europa than does on Earth. So it's actually, you can imagine, I mean, this is not totally crazy, that there could be whales, there could be real large life underneath the surface of Europa, and the only way to know would be to send probes to Europa. So this is one reason why it's exciting that we're sending probes to Mars that are so advanced, because one day maybe we can send a similar probe to Europa. It's going to be more expensive because we need to somehow drill down beneath that thick ice sheet and then send like a submarine on it. So that's kind of difficult, okay? But it's actually a really exciting potential place for life in the solar system. And it's not just Europa. That's what's even cooler, is that there's similar evidence for subsurface oceans on both Ganymede and Callisto. They're not as warm on the inside. There's not as much tidal heating because they're further away from Jupiter. But there does seem to be evidence that you go down deep enough, it's a lot of ice, and it gets warmer when you go deeper. There's liquid water. Okay, so there could be large subsurface oceans of liquid water on these moons, but in many ways these are like terrestrial planets. they're far from the sun, they're kept warm by tidal heating. So these are really exciting. Galilean moons, kind of the most interesting, some of the most interesting objects in the solar system. Gets less interesting as you go past Jupiter, but Saturn has a couple really interesting. So Saturn has this really large moon, Titan, larger than our moon. There's a picture of it. It has very thick atmosphere, so it looks orange, kind of like Venus. But underneath that atmosphere, what we see is really exciting. There's also some exciting ones I'll talk about Enceladus here. So by the way, Saturn, of course, has a very large ring system. So there's a picture of Saturn, and we have names for the ring systems, A through F. And then we have all of these moons: Mimas, Enceladus, Tethys, Dione, Rhea, and so on. Titan is the largest moon, and but it has, of course, many moons. We've detected more than 80. But the most exciting is two are Enceladus, because it has something similar going on at like Europa. So if we look at this moon, what we see is, again, not very many craters. So something, I mean, it looks like ice, has a surface of ice, just like Europa, but has ice volcanism. We actually see evidence of plumes of stuff coming out. Clear evidence of ice volcanism, and clear evidence that ice is kind of warming up and then refreezing on the surface. You can actually see patterns of this on the surface, indicating pretty clearly that there's probably a subsurface ocean on this planet as well. This moon as well. So it's another exciting potential place for life in our very own solar system. Here's an image showing the so-called Tiger stripes, which is just, if you look carefully, you see fresh ice, regions of very fresh ice that have been brought up from the warmer interior. Again, this is an example of what we call ice volcanism. That is, flows of warm, kind of bushy ice acting almost the same way as lava does on Earth. Here is this outgassing I described. So you actually see plumes of stuff being ejected like geysers coming from the surface because of the warm material. Here are the tiger stripes I mentioned. So here you see some older surface with craters, but here you see new surface with new ice paving over craters. You see that this region must be warming up and then refreezing. And you see kind of evidence of thinner ice here in blue. It's very exciting. Another really exciting moon, the other big one for Titan, for Saturn, is called Titan. And Titan was the one, if I go back, that it looks kind of orange. It almost looks like Venus, has a very thick atmosphere. But if you look below that atmosphere, using, say, radar, you actually see something that looks, wow, it almost looks like Earth. What you're seeing here are actually lakes and rivers on the surface of Titan. Okay. In fact, you see like little bays and estuaries, inlets, and so on, and islands, exactly like you see on Earth. You see erosion and weather. It's amazing. Here is another picture that's showing lakes on the surface of Titan. Now, Titan is very cold. Okay, you can't have liquid water. There's another picture of these lakes on the surface of Titan. It looks exactly like you see a lake on Earth. Okay, but instead of liquid water, you have liquid hydrocarbons. Okay, that is liquid gas-like stuff. Okay, and so the temperature on Titan is a lot colder than it is on Earth, but you have clouds and rain and rivers and lakes. But just instead of water, it's a different liquid. It's a different liquid hydrocarbons. Here's another picture showing these reflections from the sun from these lakes underneath those thick clouds of Titan. So this is another place where we wonder, this would be a perfect place for life, but it would have to be a new kind of life that we don't know about, one that doesn't live in liquid water, but that lives in liquid hydrocarbons, like basically liquid gas. Okay, possible. We don't know, and it's fascinating. And so another place where really exciting if we send a probe down to land on Titan. So this is why you should hope that we send just a tiny bit of our tax dollars to NASA so in the future send probes to this exciting place. And we've mapped out the terrain on Titan, lots of similar stuff that we see on Earth. Okay, you see lakes, craters, and dunes, and hilly regions, plains. We can map it all out. It's very similar to the sort of different types of terrain that geologists are going to have on. So after we leave Saturn, it gets less interesting. Now, currently, it's so far away, we don't have as good an idea about what the deals the moons are out here. But generally, there's nothing super exciting. Here's the main moons of Uranus: Puck, Miranda, Ariel, Umbriel, Titania, Oberon. Probably, if we could get better probes out there, maybe we'd learn new exciting things about these moons. But so far, it's cold and far away, dark out there, farther away from the sun. Here's Miranda. So we have gotten some nice up close pictures for some of these. Tallest cliff in the solar system. Okay. Rings on Uranus, just like around Uranus, just like you see from Saturn. There's the pattern of rings orbiting the regular. Triton is interesting, right? Triton is really far out. Remember, this is one of these 3 exceptions in the solar system. It's an irregular. Okay? Triton is really far out. It's exactly the sort of thing you expect to see from a captured asteroid. Remember, Triton is unique in that it's a fairly large moon that is orbiting clockwise rather than counterclockwise. So we call that retrograde. Neptune has some very, very far out moons. So some of the furthest out moons in our solar system, is indicating just how far they get from Neptune, indicating some just captured asteroids is most likely. I want to talk about the range of Saturn in particular, but it's getting to be about an hour. It's probably a good place to stop for a day. So are there any questions before I let you go? All right, if there's no questions, I will see you next Monday, and we'll come back to finishing this lecture by talking about rings of planets, in particular Saturn.
Have a good day. Have a good day, Professor.
Can you tell that thing to come on and get his iPad? He didn't go to class.